So a lot's been going on, but at the same time, on the HDD side, there's been extreme consolidation. At one point, there were over 200 HDD suppliers, and by the turn of the century, by the time we got to 2000, we were down to 10. And now to today, there are 3, right? So there's huge consolidation in this area. At the same time of all this activity, there's a very different trend going on, and that's around the consumption of nearline drives within the hyperscale. What's interesting is the original hyperscale architectures were arrays of generic servers, all optimized around performance, about getting that transactional tier to meet the needs of early search engines, early social media, online shopping, right? It was all about that transactional performance. And SSDs were really a really good fit. I mean, SSDs actually made it happen because otherwise, that transactional tier would have never gotten there. But then over the years, that technology has matured and evolved. You can see just by the search engines and social media, right? A lot has happened, and it converging with things like analytics and video. All of a sudden, the focus of the data center architectures is changing from high performance to more capacity optimized. Now, I'm not saying that performance isn't important. That's not the case at all. It surely is. But the capacity demands are increasing way faster to be able to support these needs. Video is a big dynamic here, and it comes in the form of many different pieces, whether it's social media with TikTok and Facebook Reels, things like that, but also surveillance, right? Surveillance. I mean, there are cameras everywhere. Cameras at the intersection, cameras at the gas station, cameras at your home, and all that has to be stored, right? And so HDDs are the logical choice, mainly because of their cost per capacity. And this is measured typically in dollars per gigabyte, and there's a big discrepancy between the dollars per gigabyte of an HDD compared to an SSD, and that gap is forecasted to be maintained over the foreseeable future. Will it always be maintained? Well, probably not, but the next 10, 15 years, it surely will, and it's probably going to grow from what we see today with advances in recording technologies like HAMR and things like that. When I was putting this together, it was interesting. I pulled up a couple quick data points, and a couple are kind of interesting. It's estimated that 413 petabytes of video is recorded and stored in the cloud every day. I mean, that's a staggering number. YouTube estimates that 720,000 hours of YouTube videos are uploaded every day. Right? I mean, these are staggering things to think about, but they're almost incomprehensible. So what does that mean? If you back into what that means in terms of consumption of drives, that would be an average of 142,000 HDDs a day that are being consumed by the data center, right? And that number's growing, right? So it's trends like this that are shaping the future of storage. So when as I was pulling this together, I said, well, I haven't seen the data. The data doesn't jump out at me, right? Because if you read, the typical reports and look at the data, what jumps out at you is the massive growth in SSDs, and it should, right? They are growing, but what doesn't jump out at you is the growth in nearline drives. And so I worked with Trend Focus, and I was able to pull some of this data out. And the first thing that I noticed was that it's estimated that 89% of all the storage shipped into the hyperscale last year was HDD based. Right? That's a really big number, and it's forecasted to grow. If you look at the actual data combined with the forecast data, you'll see that from a unit perspective, the graph on the top, it's growing steadily, and it's actually growing at a fairly high rate. They're estimating the growth between 2020 and 2026 to be in the order of 14%. So that's double-digit compounded growth. So that's actually quite a bit of growth. And then if you look at it in terms of capacity, it's even more exaggerated, right? Because you compound the unit growth then with the capacity advancements, and that number grows, at 32%. So those are big numbers. So, what's enabling some of this growth? So there's a combination of the pressures being put on the hyperscalers, and then the hyperscalers putting pressure on the storage ecosystem to be able to accommodate this. And so there are a handful of features that I want to talk about today that are enabling this. The first one is shingled magnetic recording, or SMR. This is a CapEx play, so it's all about increasing areal density, increasing capacity, buying fewer drives, and getting that same capacity footprint. And I'm going to go into a little more detail on each one of these and how SAS relates to them. And then there's the next one is, I call it next generation SMR. Some people call it hybrid SMR. The drive vendors might refer to it as domains or realms, but I just call it generically next generation SMR. And this is largely an OpEx play where it's about SKU management, where you can buy a drive and then format it how you want. And again, we'll talk about it in a little more detail. Then there's repurposing depopulation. This one's interesting because it was originally defined as a performance play, but has now become a very powerful feature in that it also has CapEx and OpEx implications as well. Multi-actuator, today we think of it as dual actuator. It's a performance advancement, and we'll go into more details on that. And then command duration limits, or CDLs, is another performance vector. So I'll go into a little more detail. Shingled magnetic recording, or a lot of people just refer to it as SMR, is a recording technology that aligns tracks in a more efficient manner. So if you look at the bottom, just a very kind of a cartoon diagram of what's going on. In a CMR drive, the tracks are spaced by a little bit to give it some room to be able to do the reads and writes. In shingled magnetic recording, the tracks are overlapped slightly. And this gives, and you can imagine that by compressing those tracks, the areal density increases and the capacity increases. The capacity increases are debatable and are evolving. The drive vendors all kind of claim something a little different, but there is an advantage. This all comes at a cost, however. It's not free, right? So what does it mean? It means sequential writes. And depending on your workloads, if you have full control over your workload and you know all you're going to do is sequential writes, this is awesome, right? But if you have random workloads or potentially random workloads, right, it takes a little more work, and there's knowledge of managing those zones and how those tracks get laid down to be able to pull that off. From a standards perspective, T10 standardized it with ZBC, or zone block commands. And at the same time, T13 standardized it with ZAC, or zone ATA commands. And then T10 did the translation between SCSI and ATA with SAT4. There are three types of SMR. The first one's drive managed. That was kind of the early test vehicle. The problem with drive managed, and it was a good idea, right? Drive managed SMR, the drive manages everything. So the user, the application, they don't have to know anything about it. You just get the areal density advantages. Sounds great until you start running, random workloads, and then the drive really struggles. And so what that ends up showing is that the performance of the drive is workload dependent, and that's just a non-starter in the enterprise. So in the enterprise, that was pretty much discarded. Host aware is another one. This one was kind of a tweener. The host knows about it, but doesn't need to really manage it, and so there's too much variability. Same thing, the enterprise discounted it. Then host managed, and that's where we are today. So this means that something above the drive, whether it's the OS, whether it's the application, they have to understand, they have to do the zone management, so they have to be aware of it. So what that means is, if you're a server OEM, this is a non-starter because who knows what's going to run on your server, right? You could run a whole bunch of different OSs and who knows what applications, so it's just too unpredictable. But if you're a big data center where you own the application, you own the OS, you can modify things to then take advantage of this and gain the aerial densities of SMR. Then there's, like I said, advancements in SMR. Some people call it hybrid SMR. So many different names, so you just have to be a little careful. And this is about formatting the drive. So the drive can be formatted either as a CMR drive or an SMR drive. So if you're a big data center, you buy one drive, and then depending on where it goes in your data center, whether it's a warm tier, cold tier, whatever, then you can format it as you want and then use it that way. So it's a SKU reduction type effort. And in T10, that was standardized in ZBC2. T13, ZAC2, both of those standards are complete today. The translation between SCSI and ATA has not been done yet, and that's still kind of in holding. Then you take this all one step further, this capability of formatting the drive. What if you did it dynamically? What if an example might be in my data center, I deploy the drives like out of the box as CMR drives, and for a nearline type drive, and I use the drive to its fullest capability from a performance perspective. And then as the data is getting cooler and cooler, then the drive can be formatted as SMR. So maybe half the drive then is SMR and half is CMR. And eventually the drive contains all cooler data, and the drive would then be formatted as SMR. Now, that sounds great, but the challenges of doing that would be pretty difficult. But there are customers that are looking at doing this. Again, it would have to be a true data center customer that owns their own data center, that owns all their own tools and everything, to have the capability to do that. That sounds like a big challenge, but we'll see how that goes. The next one that I wanted to talk about is repurposing depopulation, or a lot of times we'll just refer to it as depop. It was originally conceived as a performance, like I said, a performance play. The fact that IO errors can be corrected on the fly, not all, but a lot can, that's good, right? That's a really powerful tool that is used a lot. The problem with it is it's not for free, right? It takes time. So if an IO, is in error, it has to be corrected. The effect is the latency on the return is going to be a lot higher. And there are service level agreements in these big data centers where they have to guarantee that IOs are going to be served in such a time. And if you start adding, a whole bunch of correctable errors, your latency is going to get too big, and you're not going to be able to meet your SLAs. And so if a platter starts throwing a large number, there's call it a concentration of correctable errors, that is flagged, and typically what happens is then that drive gets taken offline. It gets taken offline, and your data center is then over provisioned with extra drives, and then the data gets offloaded onto the new drive, and the new drive's brought online. A couple problems with that is, one is you have to over provision your data center with a whole bunch of big drives. Today you'd have a couple hundred, extra 20 terabyte drives laying around, right? And the data center doesn't want to do that. The other problem is, somebody actually has to do that, right? The drive's going to be down. It's going to take time. It's a lot of data to move. And then somebody's got to go in and get that drive. What the drive vendors found is that when these drives get returned for these types of problems, concentrated media errors, what they found is only one platter would be the problem child, if you will. And so it's very inefficient to pull the whole drive and put in a whole new drive. I mean, the drive vendors probably like it. Well, they don't because it's an RMA. But so what if you could issue, have a new set of commands such that if you identified a platter with a concentration of correctable errors, you go and take that data and put it on another platter, and then logically depopulate or remove, take offline that one platter. So example, if you had 20 terabyte drives with 10 platters, and you then depopulated one, then the drive would just report it as a 18 terabyte drive. And so it has some very strong value propositions behind it. T10 standardized this with so this one is fairly complicated, and it has fingers like well through the SCSI stack. As you can see, it was standardized in SBC 4 and 5, and then ZBC2 had a piece of it, and then the ATA translation is defined in SAT5. The next one, multi-actuator technology. Most people refer to it today as dual actuator because that's what's out there right now. You can see in the middle diagram that's a ripped open picture of a single actuator drive where you have one actuator hooked to a group of arms. Those arms are all connected together and they move back and forth across the media. The limiter of the I/O performance of that drive is that read head, and you can only use one at a time. So you go to the picture on the right, and I know it's a little tough to see, but you can see the two arms. So now you have two actuators and two sets of arms that move back and forth across the disk, which effectively doubles your I/O performance of the drive. And from the drives that have been tested to date, it is almost a pure doubling of the performance. SAS is really well suited for multi-actuator technology because SAS has the notion of multiple LUNs. So you can map an actuator, each actuator to a LUN. So today it's two actuators, so each drive then exports two LUNs. And it's seamless. SAS does it just because it's SAS. It's really quite easy. The problem comes in some very large RAID architectures that are out there. You may have the base assumption that each drive is a LUN, and that then the whole thing goes sideways because you can't. Just the notion of having two LUNs per drive, it's not workable at all. So that's a problem. And also SATA, right? SATA doesn't have the notion of multiple LUNs, so they're in kind of the same boat. So in light of that, there have been two proposals made. One I refer to as split LBA or split LBA space. And then the second one is using a striped method to be able to export these two LUNs these two actuators as a single LUN. The one that's gotten the most traction is the one I call split LBA space. T10 calls it concurrent positioning ranges, and it has been standardized in SBC 5, ACS 5 and 6, and then the ATA translation of SAT5. And that's in testing. I'm not sure if any single LUN drives, multi-actuator drives have actually been shipped in production, but they are in test and it is being worked. We talked about dual actuator technology as being a performance play. So to be really clear, right, it's not to compete with SSDs, right? That's not what it's doing. What it's doing is trying to address the IOPS per terabyte problem or the capacity, the performance per capacity point. And we're going to talk about that a little bit on the next slide. Within the data center, they have all these metrics, right? One's IOPS per terabyte, but another one is power per capacity, right? They're very sensitive of these different metrics. Sometimes it's power per slot, sometimes it's power per capacity. Power per capacity is kind of taking over. And some, if I would call it weaknesses, concerns of dual actuator technology or multi-actuator technology is the first one's power. The power is higher, right? If you compare a single actuator drive to a comparable dual actuator drive, the power is higher on the dual actuator drive. How much? Talk to the drive vendors. It is being worked, but it is a concern and has been voiced publicly by some of the hyperscalers. Another one is capacity. Today, and I'm sure this will get resolved, but today you have to remove a platter for that extra actuator, for the extra mechanicals. So now you're going the wrong way on both those metrics, right? You're increasing the power and you're decreasing the capacity. So that has some of the big hyperscalers a little on edge about this technology. Again, keeping in mind that it's there to address the it's there to address the IOPS per terabyte issue. And this is an interesting one. As these drives get so big, but the conduit to it, the I/O processing capability of the drive stays exactly the same. It doesn't get any bigger. So the capacity behind this small pipe then can get stranded. Seagate's published a couple papers, and they call it stranded capacity. and so what everybody's metric is for IOPS per terabyte, what's acceptable, what's not, that's up to them. That my purple band would move around for different hyperscalers. I'm using this as an example where 10 would be my target. I want an IOPS per terabyte of 10 to be efficient in my data center, and then I'd call 4 my minimum. And this is just my example. It's not, there's nothing hard and fast about this. And so, for this example, you can see the 8 terabyte drive has an IOPS per terabyte of about 10. And as that drive grows, then it starts falling down because your pipe isn't getting any faster, right? You're still same I/O processing capability. And so your IOPS per terabyte starts dropping until it gets to that minimum, at which point you need to do something. Whether you implement it discretely, which some data centers have done, or you leverage dual actuator technology and you take that same 20 terabyte drive, you go dual actuator, and now you move up, closer to 10, closer to the sweet spot of your IOPS per terabyte. But you can see then you're on the vicious treadmill because then the drive gets larger and you're gonna hit that minimum again, and then maybe multi-actuator, more actuators. That's, but that's down the road. This gives you an idea. Again, this is not to solve a pure performance problem. It's not to address, the transactional tier. SSDs do that just fine. And it's not to address the cold or archival space, right? Just the biggest single actuator drive you can get, the biggest, cheapest thing you can get is good down there. This is for this nearline space, this warm space of, where photos are stored, video is stored, where all the analytics are done. You have to have the data there available to do those analytics, things like that. That's where this technology is focused. And then command duration limits, or CDLs. This is a relatively new feature. You might hear about this. People refer to it as OCP fast fail. OCP first started talking about this, maybe 2017, 2018. There are a couple good papers online on it. It's fairly interesting reading. And then T10 took it and took OCP fast fail and had to give it a new name, so they called it command duration limits. And they standardized it in SPC6, and that is nearing completion right now. CDLs give an ability to control the I/O latency in an architecture. The different knobs are fairly complex, but to kind of make the point, I used a very simplistic concept where I issue a read to a drive, you can see on the lower left, and then I expect that latency, that read to come back in a certain amount of time. And the average latency you can see on the red line on the bottom, it's fairly linear and increases with queue depth, which you'd expect. And I'd typically be running at a higher queue depth for higher performance. The problem is that we go back to the discussion we had on Depop, where there are other things that are happening, whether it's garbage collection, whether it's correctable errors. There are all sorts of things that can increase the latency of these IOs. And so to meet the service level agreements of the data center, you can't just look at the average latency. You got to look at what they call the 99th percentile latency, right? Including almost all the outliers, 99% of the outliers. And what you see is if you plot that, you get the blue line, which increases much more dramatically with queue depth, right? So you can imagine you get an IO error and you have this big queue, and now everything gets backed up behind it. And so the higher the queue depth goes, the higher that number gets. And in fact, at a queue depth of 32, it's like a 3x increase. And that's what the hyperscalers are going to be dealing with. And so how can you deal with that? what if you had the data on 3 drives? And this is my example, my simplistic example. We have the data on 3 drives. I issue that same read to all 3 drives. And now, again, there are different knobs. Some are certain timers, active timers, inactive timers. But just for the sake of this discussion, let's say I just want the data back as fast as I can get it. And so then I issue that read to those 3 drives, and one comes back first. And then the other 2, I fail. I fail those reads. And so, nothing bad happens. It doesn't report it as a problem. SCSI just says, okay, well, he failed those 2 reads, and you move on. And then if you look at the data on the right, we use that same plot where the red is the average without CDLs, the blue is the 99th percentile without CDLs, and then the green is the 99th percentile with CDLs enabled. That's pretty impressive, right? So the 99th percentile with CDLs enabled is lower than the average with CDLs disabled. And I have to credit Damien from WD, helped me with some of this data. He presented a paper at SDC last year on this much more in depth on this topic. And so if you're interested, I credited, and you can see the name of the paper in the notes. So in summary, you can see that the capacity demands are increasing dramatically within the hyperscale data centers. HDDs are a great tool for it and will continue to be a great tool for it for years to come. Again, maybe not forever, but for the next 10 to 15 years, they're definitely play an important role. And SAS, with its native scalability and innovative features, is very well positioned to enable this type of growth. So I am part of the SCSI Trade Association. I invite you to follow us on social media and visit our website at www.scsita.org. Any questions?
So the availability of 24G SAS infrastructure now is...
It's there. Yeah. Yes. Yes, Kioxia and Samsung have made public announcements on their drives. Now, and those are 24 gig SSDs, right? And to be really clear, yeah, right. And so that's a good point, right? And I had this discussion with Cameron Brett, who's the president of the SCSI Trade Association from Kioxia, and he was concerned, well, wait a minute, all you're talking about is 24 gig SAS and the innovations in SAS relative to HDDs. But I should state that, my pitch was about innovations in the hyperscale, not so much on SSDs and performance, but it does exist, right? And it's very important in SSDs.
Like CDL could apply to SSD.
You bet. Oh, and so you're absolutely right. And another one, and I think it's in the slide on Depop. It says that it's relevant to SSDs and HDDs. Where'd it go? Bottom last bullet. Standard applies to both HDDs and SSDs. Nobody's using it as far as I know for SSDs. But I mean, you could think about it, right? If you have a bad NAND, die or something, and you could discern that, then you could just depop that particular die.
Actually, I'll have to challenge this idea.
Okay.
As a storage array vendor, repurposing a drive in place and reformatting it at lower capacity, that's really tricky to do.
Yes.
I mean, it can be done, but then you have to ask, is the head on platter 3, is it actually still attached, or is it just not working? Those kind of questions.
No, so again, most of these technologies are very focused on a data center environment where you own the OS, you own the tools, you own the applications, everything. SMR is a good example. You go talk to a Dell or an HP and say, hey, you're going to do SMR, and they'll just roll their eyes, right? Because you could never do that because it's so specific. And maybe I make this sound like, oh yeah, you just do this, this, and this. Yeah, no, there's a lot of work for most of the stuff in the background that's got to be done. You bet, right? You can't just go take a drive in your infrastructure and say, oh, now it's 18 terabytes, right? Yeah. So I need to correct you. OCP plays a really large role in HDDs, huge. I mean, so there's NVMe HDD subgroup. There's, and I forget what it's really called, but it's about mechanicals and vibration, right? To be able to, because you can imagine these huge arrays with hundreds of drives, and they all have 10, maybe more platters, and everything's moving around. There's a big effort on vibrations and acoustics, and OCP's driving all that. So OCP plays a big role. Actually, I mean, so this came from RDP came from OCP, CDLs came from OCP. So there's a lot. So am I missing the question? I mean, so you go, you talk to Jason Adrian from Microsoft, Madhavan from Facebook, a lot of these guys. And yeah, it's not and so that's another point of this presentation, right? Is it's not the fun stuff to talk about, right? People want to talk about Flash and the cool advancements in Flash. And it's very important. Don't get me wrong, it really is important. But there's also a really big thing that's going on in the background. And OCP is very involved in it. And I mean, you go and, when I was putting some stuff together for this, there's a paper, I think Google did it from 2016. I can look it up for you because I read it for this presentation, talking about the HDD's roles in the data center. And this is 2016, and they were saying, well, what if we did some of these things? It was very way out there. So if you read it in 2016, it was one of those papers that you read and it just doesn't make any sense because it's so far out there. But you read it now and you're like, oh, well, okay, that's not exactly what we're doing, but that does make sense. So it's an interesting research project. So that's what I found when I put this together. So. No, and so I get asked that a bunch. Why doesn't everybody just use SSDs? And you get into the cost per gigabyte, cost per capacity argument. But even that aside, it comes up article after article. Even if you abandoned everything and said, okay, we're going to do everything in Flash, the Flash capacity, couldn't touch what the demands are out there in terms of the capacity needs. And even if they started ramping up capacity now, they wouldn't be able to meet the capacity needs for another 10 to 15 years. No, eventually, HDDs probably will go away. But I mean, look at tape, right? I mean, we've been saying tape's going to go away for 30 years. And I just read an article about the importance of tape in the data center. Another thing that's interesting is, and I touched on it early on, it's about analytics. These data centers have to monetize their data. Right? I mean, they're not doing this for free, right? So they need to make some money. And so if they're gonna do analytics on the data, they need it warm. Can't be on tape or optical drive or something, maybe like the olden days. It has to be available and has to be usable. They have to be able to go and look at it. So, any other questions? So it's good. It's very good, actually. And one of the, so I'm with Broadcom, right? And so we have our 24 gig lineup, and it's very impressive the adoption with the data centers. And it's not because they're talking to 24 gig drives, right? It's because of security, right? So we've added all sorts of, and not just we, I'm sure Microchip would say the same thing. They've added, we, the ecosystem, have added all sorts of security features that are paramount to these new data centers. Security's one. Bandwidth aggregation, right? They're gonna be using SATA drives, whether we like it or not. They're gonna be using SATA drives because of that cost per gigabyte metric. And with bandwidth aggregation, they can still fill their 24 gig pipe. So they can be very efficient in the connection from, whether it's, in a traditional architecture, a RAID head node to your JBODs, or in a more of a storage server. Still, it's much cheaper to route, a 24 gig pipe than it is, a 6 gig pipe, or, wide 6 gig pipe. So there are a number of things that are driving 24 gig into the hyperscale data center, not necessarily specifically 24 gig to the drive. And so it's been a big pull for us. And there are going to be some announcements probably around OCP Global Summit next month that will be relevant as well.
Can you juxtapose, because you're really focused on hyperscale data center.
This article, not.
Can you juxtapose the 24 gig story versus like CXL? I'm sure that's above, right?
I'm not sure how.
That's fine. I get that. It's still kind of new.
Yeah. So the big question is, CXL's relevance in storage. And when I say storage, I mean all the way out at this end of the storage. Not so much in the box, talking to GPUs, that's all different, right? That's different. But out to the drive, it's still not clear what CXL's role is going to be. Could there be something? Yeah. Combining storage and memory on a fabric, maybe, but not.
Well, the CXL Holy Grail is the PCIe scale out, which is, I'll call it a memory access network, right?
Yeah. Oh no.
Area network.
On paper, that would be the Holy Grail. That's awesome, right? One, and I'm wearing a SCSI hat, right? I'm wearing a SAS hat, right? I deal with both, but up here I'm SAS. My question would be, and you said it, scalability, scale. How do you scale PCI? Yes, PCI, NVMe over fabrics, things like that. But remember what you're competing with. You're competing with, a couple expanders with 100 drives. Try to do that with NVMe over fabrics, and you're into it you're into an Ethernet switch. I'm using Ethernet as my fabric. Ethernet NICs, PCI switch, which is, right, much more expensive than a SAS expander, right? It gets complicated very quickly. So, good conversation. Anything else? Okay, thank you.